In this video, we're going to look at an application of this summation notation, which is a concept that you're probably familiar with, which is taking the average, in other words, the mean. But we're going to dig into some details that might not be so obvious. Well, first of all, in formal textbooks and stuff, the formula for the average, or the mean, is something like this. Now, most people who know how to take the average of a few numbers, add them up and divide by how many there are, will look at this formula and be like, what is this formula saying? But if we break it down, so this formula, which is 1 over n times the sum of xi, which also could be written as the sum of xi divided by n, is just saying this. N is the number of numbers that you're trying to take the average for, and the numerator here is just adding each of them up. So the sum of xi, as I goes from 1 through n, if we were to write it out, that's just like x1 plus x2 plus x3 all the way through xn divided by n. And x1 in statistical notation is talking about the first observation. x2 is talking about the second observation. There's no relation to that being the number 2 or anything. It's just the second observation, the third observation, the first observation, right? That's all x subscript I means. It's the observation number I. So let's do a straightforward example. Let's say you're given this data set that x1 is 3, x2 is 4, x3 is 6, and x4 is 7. And the question is, find x bar. X bar, by the way, is a notation to indicate the mean of a set of numbers. In later statistical stuff, you also use mu for the population mean, but that's for a different video. So x bar, let's see, let's just apply the formula. That's literally just going to be x1 plus x2 plus x3 plus x4, because there are 4 of them, right? x1, x2, x3, and x4. There's 4 of them, so the sum of all the x's is just adding those 4 up, divided by the number of them, n. There is 4 of them. And so that's just going to be, let's see, x1 is 3, x2 is 4. So it's really just 3 plus 4 plus 6 plus 7 all over 4. 3 plus 4 is 7. 7 plus 6 is 13. 13 plus 7 is 20. So long story short, that's just 20 over 4, which is 5. All right, so the average of these numbers is 5. One thing to notice is that the average doesn't actually itself have to be in the data set, right? The numbers, none of these were 5, but the average of them was 5. All right, that's pretty straightforward. Let's say that you were then given this data set and asked to do the same thing. So here, really just add them up and divide it by how many there are, right? There's 1, 2, 3, 4, 5 numbers. So let's just add them up. -3 plus 2 plus 1 plus 4 plus 6 divided by 5. Pretty straightforward. These add up. -1 plus -3 plus 2 plus 1 is 0. Plus these 2 is 10. So this is overall 10 over 5. Or you could just plug that all into a calculator and you'll get 2. So the average of these is 2. Now what if, on the other hand, I gave you this data set and said to find the median instead of the mean? What is the median? Well, the median of a data set is essentially the middle number when they're arranged in order. And so here, it might be really tempting to look at this and say, oh yeah, the middle number, there's 5 of them, so the middle number is 1. But that's failing to take into account that they're not in order. Because in order, they would be, let's see, -3 is the smallest one, but then 1 is after that, and then 2. So the 1 and 2 here should be reversed if we wanted to put them in order. And so once we put them in order, now the middle number is going to be 2, so the median here is 2. So the median, again, of a data set is the middle number when they're put in order. Now, when there's an odd number of numbers like this, there's only one middle number, and so that's your median. But if there's an even number, like if we had one more number here, like a 7, well now there's 2 middle numbers over here, right? That split it, like there's 2 numbers here, 2 numbers here, so that's an equal distance. And then so in that case, you just average the 2 middle numbers. If there's an even number of numbers, you've narrowed it down to 2 numbers for being the middle one, and then you average the 2 of them, meaning add them up and divide it by 2, and that will be the median of that data set. Now here, notice that the median for this data set was 2, and the mean was also 2. Now the mean and the median don't actually have to equal to each other, and in fact there's some implications for when they're not equal to each other. while we're on this note, the third measure of central tendency is called the mode, and that's just the most frequent observation. So let's say you want to try to find out what's the average income. And so you asked a bunch of people what their income is, and you put it in order, and these are the numbers. And so you're wondering what is a good way to report the, average income? Should you say mean, median, or mode? Well, let's take a look. Here, the mode, the most frequent observation is 0, because 2 people said 0, and no other observation had 2 different people saying that, right? So the mode here is 0. All right, so the modal income is 0. Now, if we're thinking about it, it's like if this is representing America, that's actually true. The modal income in America is 0 because people report incomes to the units digit, and so there's very few exact numbers where so many people have that number. But every unemployed person has an income of 0, and so that ends up being really common. And so, but is that really representative of what we want? And so, not really, right? And so, the mode in this case is probably not that good. What about the median? That's just the middle number, right? So out of these 7 numbers, there's 3 to the left, 3 to the right, and so the middle number here is 60,000. So that's the median income. The median of these 7 numbers is 60,000. What happens when we try to take the mean? Here, if we were to just add them up and divide it by 7, look at the rightmost number here, 10 billion. You probably got like Bill Gates or somebody in your sample. And so if you were to add these 7 numbers up, they're going to be pretty close to 10 billion. And when you divide it by 7, that's going to be like a little over 1 billion, right? So the mean income is like roughly 1 billion, like a little bit more than 1 billion, right? So that's not representative. And so what this is getting at is this point about the difference between the median and the mean, which is that the mean is influenced by outliers. So if you have a value in your data set that's really large or really low compared to the rest of them, the mean will be very influenced by it. It'll even maybe go so far off that it's really not representing most of the data points at all, and really just representing that extreme point or something in between. Versus the median was totally unaffected by the outlier. Here, if this 10 billion were instead 1 million, I mean, that'd make a huge difference for what the mean is, right? The mean would then be something a lot smaller, but the median literally would not change. It would remain 60,000 because that's still the middle number. So again, it's not saying, so really in each context, you have to pick which measure of central tendency you think is representing what you actually want. Finally, let's talk about this thing called expected value. Now, when you learn how to take the average, you're like, oh yeah, that formula, right? Add them up, divided by how many there are. But then when you get into more statistics and stuff, there's actually a more grown-up way to take the average. The grown-up way to take the average is what we call the expected value. And the formula is this, that the expected value, E of x, which in our case is the same as x bar, is essentially the sum of x times the probability, P of x. And so what that's saying is this, is you take each data point and you multiply by how frequent it is. What's the probability of getting that x value? And then you add them up. And that's essentially a way to find the average. So let's apply that and see what that means. So let's say here, you're given a list of, let's say you want to know what's the average number of classes that students at my university take. And let's say you have this data that how many people take exactly 2 classes, and this column is giving you the percentage, so 30%. 30% of people at your university take exactly 2 classes. 50% take exactly 3 classes. Another 15% take 4 classes, and 5% take 5 classes. And if you add these up to 100%, right? So that's the thing here. Here, these percentages have to add up to 100% of everybody, right? So long story short, you're basically trying to average a bunch of, 2s, 3s, 4s, and 5s, right? Because people either take 2, 3, 4, or 5 classes. And if you have thousands and thousands of students, you're just going to add up how many classes are you taking, add them all up, divided by how many there are. But here, this gives you a much more compact way to do it. You're basically saying, all right, 30% of the people are taking 2 classes. So you're saying essentially the number 2 classes, gets a weight of 0.3. Then 3 classes gets a weight of 0.5, because that's 50% of people are taking that, right? And so on, right? So here 4, so again, that's really what this formula is. It's like you take the x, you multiply it by its probability, so 2 times 0.3, and then you're adding it. So you're adding that with 3 times 0.5, then you're adding that with 4 times 0.15, and so on. And when you're done writing all that out, you can plug that into Google, for example, and when I did, I got 2.95. So 2.95, that is the average. That's the interpretation, is that that's the average number of classes, which kind of makes sense. Here, most people take 3 classes, and there's some that take less and some that take more, but more people, only 20% take more than 3 classes, and 30% take 2 classes. So when you're averaging them all out, it makes sense that it's going to be close to 3, but that it's going to tip a little bit less than 3, just a little bit, because more people take less than more, But so that's what all this is. And just to give some intuition behind why this formula is the same as, the regular add them up and divide by how many there are. If I were to just tell you, suppose that you're just a really simple, suppose you just wanted to average 3 people's, value for something, and their values were, let's say, 10, 12, and 15. The old school way, you'd add them up and divide it by 3, but just to give you a sense of why this formula still works and produces that same answer, is here you'd say that, all right, here 1/3 of all people have a value of 10, another 1/3 of all people have a value of 12, and then 1/3 of all people have a value of 15. And when you do this formula out, the expected value formula out, you get 10 times 1/3 plus 12 times 1/3 plus 15 times 1/3. And basically, these all have the same common denominator of 3. So you can write this as 10 plus 12 plus 15. So algebraically, it's the same thing. So in general, it's kind of like if you have n people, each with the value of 1 over n is the likelihood of them having that person having that value, right? So when you add them all up, it's like you have 1 over n times x1, and then plus x2 times that has a probability of 1 over n as well. And so all of these have 1 over n, and you take n as the common denominator, and you get x1 plus x2. So it is the same thing, but this formula lets you answer questions when things are given in this sort of format, where you're just given probabilities.